Hello everybody, welcome back to our class BJTE 2023 Electric and Electronic Technology. Today we will look at a new chapter titled Resistance. Resistance is opposition to the flow of current. Some materials such as glass and rubber offer great opposition to current flow. Other materials such as silver and copper offer little opposition to current flow. This chapter examines the characteristics of resistance, types of resistance, and the effects of connecting resistors together by a conductor to form a circuit. Resistance. As previously mentioned, every material offers some resistance or opposition to the flow of current. Some conductors such as silver, copper, and aluminum offer very little resistance to current flow. Insulators such as glass, wood, and paper offer high resistance to current flow. The size and type of wires in an electric circuit are chosen to keep the electrical resistance as low as possible. This allows the current to flow easily through the conductor. In an electric circuit, the larger the diameter of the wire, the lower the electrical resistance to current flow. Temperature also affects the resistance of an electrical conductor. In most conductors, copper, aluminum, and so on, resistance increases with temperature. Carbon is an exception because the resistance decreases as temperature increases. Certain alloys of metals, manganese and tungsten, have resistance that does not change with temperature. The relative resistance of several conductors of the same length and cross-section is shown in figure. Silver is used as a standard of 1, and the remaining metals are arranged in order of ascending resistance. For example, lead has a higher resistance compared to copper. The resistance of an electric circuit is expressed by the symbol R. Manufactured circuit parts containing definite amounts of resistance are called resistors. Resistance, R, is measured in ohms. 1 ohm is the resistance of a circuit or circuit element that permits a steady current flow of 1 ampere, 1 coulomb per second, when 1 volt is applied to the circuit. Conductance. The term in electricity that is the opposite of resistance is conductance. G. Conductance is the ability of a material to pass electrons. The unit of conductance is ohm spelled backwards. The symbol used to represent conductance is the inverted Greek letter omega. Conductance is the reciprocal of resistance and is measured in Siemens. S. A reciprocal is obtained by dividing the number into 1. Resistance, R equals 1 over conductance, G. Thus, conductance, G equals 1 over resistance, R. If the resistance of a material is known, dividing its value into 1 gives its conductance. Similarly, if the conductance is known, dividing its value into 1 gives its resistance. Resistors. Resistance is a property of all electrical components. Sometimes the effect of resistance is undesirable, other times it is constructive. Resistors are components manufactured to possess a specific value of resistance to the flow of current. A resistor is the most commonly used component in an electronic circuit. Resistors are available with fixed or variable resistance values. They are available in a variety of shapes and sizes to meet specific circuit, space, and operating requirements. Figure on right are fixed resistors come in various sizes and shapes, and figure on left are variable resistors come in many styles to meet the needs of manufacturers of electronic equipment. Resistors are drawn schematically as a series of jagged lines, as shown in figure. A resistor's tolerance is the amount that the resistor may vary and still be acceptable. It is expensive for a manufacturer to hold a resistor to a certain value when an exact value is not needed. Therefore, the larger the tolerance, the cheaper it is to manufacture. Resistors are available with tolerances of ±20%, ±10%, ±5%, ±2%, and ±1%. Precision resistors are available with even smaller tolerances. In most electronic circuits, resistors of 10% tolerance are satisfactory. For example, how much can a 1000 ohms resistor with a 20% tolerance vary and still be acceptable? In order to find the tolerance, we need to multiply 1000 ohms with 20% or 0.20. This will give us ±200 ohms. The tolerance is ±200 ohms. Therefore, the 1000 ohm resistor may vary from 800 to 1200 ohms and still be satisfactory. For the sake of uniformity, electronic manufacturers offer a number of standard resistor values. Figure is a list of standard values for resistors with ±5%, ±10%, and ±20% tolerance. After the value on the chart is obtained, it is multiplied by the value associated with the color of the multiplier band. Resistors fall into three major categories, named for the material they are made of: molded carbon composition resistors, wire wound resistors, and carbon film resistors. Until recently, the molded carbon composition resistor was the most commonly used resistor in electronic circuits, as in figure. It is manufactured in standard resistor values. The wire wound resistor is constructed of a nickel-chromium alloy, nichrome, wire wound on a ceramic form, as shown in figure. Leads are attached and the entire resistor is sealed with a coating. Wire wound resistors are used in high-current circuits where precision is necessary. The resistance range varies from a fraction of an ohm to several thousand ohms. Film resistors have become popular, as in figure, because they offer the small size of the composition resistor with the accuracy of the wire wound resistor. A thin film of carbon is deposited on a cylindrical ceramic core and sealed in an epoxy or glass coating to form a carbon film resistor. Cutting a spiral groove through the film, the length of the resistor, sets the value of the resistor. The closer the pitch of the spiral, the higher the resistance. Carbon film resistors are available from 10 ohms to 2.5 megohms at ±1% tolerance. Metal film resistors are physically similar to carbon film resistors but use a metal alloy and are more expensive. They are available from 10 ohms to 1.5 megohms at a ±1% tolerance, although tolerances down to ±0.1% are available. Another type of film resistor is the tin oxide resistor, as in figure. It consists of a tin oxide film on a ceramic substrate and is also available in a single inline format or dual inline pin format. Surface mount resistors are ideal for small circuit applications. A thin film of carbon or metal alloy is deposited on a ceramic base or substrate. Contact from the resistive element to the printed circuit board is via metal end caps, or terminals, resulting in zero lead length. In application, these end caps are soldered directly to the circuit board conductive trace using an automated soldering process. The lack of long leads to solder into the printed circuit board yields several advantages. Among them are lightweight, smaller printed circuit board sizes and the use of automated assembly processes. Surface mount resistors are available in both thick and thin films. They are available from 0 ohms to 10 megohms at tolerance of ±5% down to ±0.1%, with power handling capabilities of 1/16 watt to 1 watt. Variable resistors allow the resistance to vary. They have a resistive element of either carbon composition or wire that is connected to two terminals. A third terminal is attached to a movable wiper, which is connected to a shaft. The wiper slides along the resistive element when the shaft is rotated. As the shaft is rotated, the resistance between the center terminal and one outer terminal increases, whereas the resistance between the center terminal and the other outer terminal decreases, as in figure. Variable resistors are available with resistance that varies linearly, a linear taper, or logarithmically, an audio taper. A variable resistor used to control voltage is called a potentiometer, or pot. A variable resistor used to control current is called a rheostat. The small size of the resistor prevents printing the resistance value and tolerance on its case. Therefore, a color-coded strip system is used to display the resistor value. The strips can be seen and read in any position that the resistor is placed. The Electronic Industries Association (EIN) color code is shown in figure. The meaning of the colored bands on a resistor is as follows. The first band, closest to the end of the resistor, represents the first digit of the resistor value. The second band represents the second digit of the resistor value. The third band represents the number of zeros to be added to the first two digits. The fourth band represents the tolerance of the resistor. For example, the resistor shown in figure has a resistance value of 1500 ohms. The brown band, first band, represents the first digit, 1. The green band, second band, represents the second digit, 5. The red band, third band, represents the number of zeros, 2 zeros, to be added to the first two digits. The silver band, fourth band, indicates a resistance tolerance of 10%. Therefore, this is a 1500 ohm resistor with a ±10% tolerance. A resistor may have a fifth band, as in figure. This band indicates the reliability of the resistor. It tells how many of the resistors, per thousand, will fail after 100 hours of operation. Generally, when there are 5 bands on the resistor, the same amount of body color shows at each end. In this case, look for the tolerance band, position it on the right, and read the resistor as described previously. There are 2 instances where the third band does not mean the number of zeros. For resistor values of less than 10 ohms, the third band is gold. This means that the first 2 digits should be multiplied by 0.1. For resistor values of less than 1 ohm, the third band is silver. This means the first 2 digits are multiplied by 0.01. A resistor may also be identified by a letter and number, alphanumeric, system. For example, RN60D5112F has the meaning as in figure. The resistor value is the primary concern. 3 to 5 digits indicate the value of the resistor. In all cases, the last digit indicates the number of zeros to be added to the preceding digits. In the example given, the last digit, 2, indicates the number of zeros to be added to the first 3 digits. 511, so 5112 translates to 51,100 ohms. In some cases an R may be inserted into the number. The R represents a decimal point and is used when the resistor value is less than 10 ohms. For example, 4R7 represents 4.7 ohms. The 5-digit numbering system is similar to the 3 and 4-digit systems. The first 4 digits represent significant digits, and the last digit indicates the number of zeros to be added. For values of less than 1000 ohms, the R is used to designate a decimal point. Surface mount resistors are identified similar to the letter and number system. The part number of the resistor is interpreted as follows. The number varies between manufacturers. For example, RC0402J103T has the following meaning. 0402 equals the size of resistor, 0.04 ins by 0.02 ins. J equals tolerance, J equals plus minus 10%, F equals plus minus 1%, D equals plus minus 0.5%, B equals plus minus 0.1%. 103 equals resistance, 3 or 4 digit code available. T equals packaging method, the resistance value is indicated by 3 or 4 digits. In either case, the last digit indicates the number of zeros to be added to the preceding digits. In the example given, the first 2 digits are 1 and 0, followed by 3 zeros, for a value of 10,000 ohms. For values of less than 100 or 1000, depending on the number of digits used, D is used to designate the decimal point. For example, 3D9 would represent 3.9 ohms. A 0 ohm resistor or jumper is designated as 000. Potentiometers, variable resistors, are also imprinted with their values, as in figure. These may be their actual values or an alphanumeric code. With the alphanumeric code system, the resistance value is determined from the last part of the code. For example, in MTC253L4, the number 253 means 25 followed by 3 zeros, or 25,000 ohms. The L4 indicates the resistor construction and body type. Thank you for listening to the presentation. If you should have any question, please feel free to ask. Thank you once again.